My name is Duriya Nabil. I am from MS Chemistry. My ID is 9 and today the topic of my presentation is cement industry. Let's start with introduction. Cement industry, a relatively fast-growing industry, is developing in pace with increasing building and construction activities. Cement is an essential building block of development. The sector has huge economic impact due to its long and diverse supply chain and contributes to approximately 0.4% to the global GDP and 7.7 to the world employment. Cement has long been used as a bonding agent to unite particles or to cause on a surface to adhere to another. Cement is a rocky powder that can be mixed with water and molded to any desired shape, after which it hardens to a rock like consistency. It is used worldwide both as a mortar to join bricks and blocks together and as an ingredient of concrete, which is a mixture of crushed rock, sand, and cement is used to construct buildings, bridges, road, pipe, dams, and other structure. Concrete is a combination of inert mineral aggregates such as sand, gravel, crushed stone, and cement. Cement is one of the most developed goods in the world due to its importance as a building material and geographical availability of main raw materials. Limestone cement is manufactured in almost all countries. Let's move to the topic, the classification of cement. Cements are broadly classified into two categories, hydraulic and non-hydraulic, depending on how they react to presence of water. Hydraulic cement. This cement gets hardened in a very short span and widely used in construction for saving times and effort. The basic components are limestone, clay, and gypsum mixed in a very high temperature to create a strong adhesive effects. The advantage of this cement is that their resistance to weather changes and even underwater conditions like tank, pools, etc. They are also non-reactive to chemical attacks, non-hydraulic cement. They have a very long setting period and can only work in a dry condition. Non-hydraulic is not practical for commercial construction as it cannot be used in a site that open to weather challenges. Made with a lime, gypsum, and oxychloride, this cement cannot be used for water-related construction and strictly reserved for indoor purposes to achieve structural strength. Let's move to the next topic, the different types of cement used in construction. Listed below are some of the most popular type of cement used in construction with brief information on the properties, composition, and uses. Ordinary Portland cement, it is in usual construction work. Ordinary Portland cement is widely used. Portland cement clinker is a hydraulic material which consists of at least two-thirds by mass of calcium silicate. The remainder consists of aluminium and iron containing clinker phases and other compounds. The ratio of calcium oxide to silicon dioxide shall not be less than 2. The magnesium oxide content shall not exceed 5% by mass. Portland pozzolana cement. The main component of this cement is pozzolana, which include materials like fly ash, volcanic ash, or calcined clay. The cement is prepared two ways: one by grinding pozzolanic clinker with ordinary Portland cement, or adding pozzolana with gypsum or calcium sulfate. Rapid hardening cement. When finely grounded, tricalcium silicate is present in opacity with higher content. It gains strength more quickly than opacity. This type of the opacity is called rapid hardening cement. Setting cement. Quick setting cement is a cement which set in a very short time. The initial setting time is 5 minutes and the final setting time is 30 minutes. The composition of quick setting cement is clinker, aluminum sulfate. The aluminum sulfate increases the hydration rate of silicate. Low heat cement, it is a special type of cement which produces low heat of hydration during setting. Some chemical composition of ordinary Portland cement is modified to reduce the heat of hydrogen. The chemical composition of low heat cement, a low percentage of tricalcium aluminate and high percentage of declaiming silicates. Sulfate resistant cement. Sulfate resisting cement is used to resist sulfate attack in concrete due to low percentage of tricalcium aluminate. The potential of calcium sulfoaluminate get reduces. Blast furnace cement. The Portland cement clinkers and granulated blast furnace slags are integrated to make the blast furnace cement. High aluminium cement. High aluminium cement is obtained by mixing calcining bauxite and ordinary lime with clinker during the manufacture of OPC. White cement. The white cement is quick similar to ordinary Portland cement except for the color. The amount of the iron oxide and magnesium oxide are low in white cement. It is expensive than opposite, so not economical for ordinary work. Colored cement. To make the 5 to 10% of suitable pigments are ground with opposite types of pigments are selected according to desired color. The cement is not always gray or white. With advancement in technology, you can now find the colored cement in the market. By mixing 5 to 10% of mineral pigment to ordinary cement, you can obtain the beautiful colored cement like blue, green, yellow, etc. Air Air entertaining cements. Air entertaining cement is a different cement variety that has addition of small amount of air entertaining agents like the glues or resins to create air bubbles in the concrete. The technique is used for increasing the cold resistance in concrete, especially when it is subjected to frequent freezing and thawing. Expansive cement. The cement expand in a volume when mixed with water compared to ordinary Portland cement. By doing so, the cement help in minimizing the shrinkage loss caused due to the loss of moisture. Hydrographic cement. This cement has a water repelling properties to avoid the loss of cement in areas affected with frequent water contact. Slag cement. It is a type of hydraulic cement that is prepared while finely grinding the granulated blast furnace slag. Presently, the slag cement is used as an alternative to Portland cement for its better workability. It has a higher resistance to chemical ratios and better comparative strength. Ultra high strength cement. This is a new variety of cement invention made as a part of the recent technological advancement. The cement is now used in developed countries like America, Australia for making the bridges and other massive structures. The ingredients used in the cement are Portland cement, silica fume, quartz flour, superplasticizers, and organic or steel fibers. Now move to the next topic, cement manufacturing process. Cement manufacturing process occur in a 6 steps, including crushing, raw meal, grinding, homogenization, preheating, and clinker production, cement grinding, packing, and shipping. Crushing. Crushed limestone and other materials are usually stored overlaid to protect them from environment and to minimize the dust. In most cases, quarries and cement plant require separated or single power supply. The crushing of cement raw material is a process to cut large particles into small sizes. The raw material of cement include limestone, clay, tripoli, and others. Limestone is always the main composition for reducing the transportation costs. Most cement plants would be located near the limestone quarry. After the raw material extraction by mining or the loaders, they are sent to cement crushers that crushes all material into smaller particles. According to characteristic of raw material, the jaw crushers and impact crushers are mobile crushers will be the best choice. Raw mill grinding. After the crushing, the qualified raw material will be sent to pre-homogenization and humid materials will be dried firstly and then sent to pre-homogenization. Pre-homogenization roughens the prepared crushed materials and corrective material in a certain proportion. In the raw milk grinding production, cement raw materials will be ground into fine size to make the sure good mixing. In this stage, there are 2 types of raw milk to choose. The vertical grind mill uses the pressure leak by cylinder to crush the passing material. The cement ball mill uses ball to grind the material. Preheating and clinker production. The diameter of the clinker ball should be between 0.32 and 5.0 centimeter. The high temperature treatment system include preheating, calcination, and sintering, and calcination is the core of clinker production. Raw material is continuously weighed and fed into the top of cyclone preheater. The material in preheater is heated by rising the hot air, and the material is converted into clinker in a cement rotatory kiln. The clinker enters the grate cooler from kiln head for thermal regeneration and cooling. The cooled clinker is then transferred to clinker silo by conveyor for storage. Clinker can be transferred on the conveyor belt after cooling and can regenerate up to 30% of the heat. Cooling air sent through clinker is fed into rotatory kiln, which facilitate the fuel combustion. The fiery corpses collected by the grate coolers consist of cement minerals which are recycled and reprocessed. This is the diagram of cement rotatory kiln and shaft kiln. According to the cooling efficiency and desired cooling temperature, the amount of the air used in cooling process is approximately 1 to 2 kg per kilogram of clinker. After the cooling process, some of the gas is used in the other process, such as a coal drying. The amount of the gas that need to be cleaned can be reduced. Clinker storage capacity can be considered based on market demand. The cement plant can usually store 5 to 25% of annual clinker production. Cement equipment such as a conveyor belt and bucket elevators can be used to transfer clinker from great coolers to the storage areas and between the clinker mills. Cement grinding. Cement grinding. The clinker is removed from clinker silo and sent to the feeding silo when it is mixed with gypsum and additives before entering the cement mill. During the cement grinding process, when the clinker is found to ground to fine powder with the other raw material, up to 5% gypsum or additional anhydride is added to control the solidification time of the cement. Manufacturers use cement crushers to obtain the scheduled size of clinker and gypsum, which is then fed into cement ball mill for the rest of grinding. Grinding process is carried out in a closed system, which is equipped with the air separators to separate the cement particles according to size. Materials that are not completely finely grounded are relayed through the system. This is the diagram for cement grinding, packing, and shipping. The finished cement is stored in a huge cement silos. Cement can be shipped to customers in a bulk by truck or cargoes or bag and sent in a standard trucks. When opening a cement plant, the delivery process is one of the most important tasks since the shipping equipment is all commonly used for weighing, unloading, and unloading the materials for external suppliers. This system must support process control for the feed transfers. Let's move to the next topic, emission from cement manufacturing. Cement manufacture cause environmental impact at all the stages of the process. These include the emission of airborne pollution in the form of dust, gases, noise, and vibration when operating the machinery, and during the blasting in quarries and limestone quarries are visible from long distance and may permanently disfigure the local environment. Cement is one of the most polluting industry. 5% of the world total emission of greenhouse gas is caused by cement polluting. Cement industry is a potential anthropogenic source of the air pollution. It has estimated the cement production originate about 5% of global man-made carbon dioxide emission. This typical gaseous emission to air from cement production include nitrogen oxide, sulfur oxide, carbon dioxide, carbon monoxide, and the volatile organic compound and particulate matters. The major pollutant can be classified into categories gaseous and particulates. Fuel combustion process is a source of gaseous emission, which include the oxides of nitrogen, oxides of sulfur, oxides of carbon, and volatile organic compounds and hydrogen sulfide. What are the environmental and health impacts of the emission? Environmental and health impacts of emission, the air pollution from cement manufacturing is becoming important environmental problem worldwide. Recent studies determine the relationship between the cement air pollution and human health disease. Sulfur oxide. The oxides of the sulfur are formed from the combustion of fuel which contains sulfur and oxidation of sulfur containing raw materials. Sulfur is present in the cement raw materials. Sulfur dioxide emission generated from sulfur in raw materials are lesser than the sulfur dioxide emission generated from sulfur in the fuel. In rotated kaolin, the raw material oxidized to form sulfur dioxide and sulfur trioxide at a temperature between 370 and 420 degrees Celsius, prevailing in the kaolin preheaters. Sulfur dioxide is formed by thermal decomposition of calcium sulfate in clinker, and sulfur trioxide is present as an anhydride and can easily be decomposed to sulfur dioxide and oxygen. But the highly alkaline conditions in kaolin can absorb 99% of the sulfur oxides. Sulfur oxides react with water vapors and other chemicals highs in atmospheres in the presence of the sunlight to form sulfuric acid. These acid form usually dissolve in suspended water droplet which can be washed from air on the soil by rain or snow. This is now the acid rain. It is responsible for much damage to life and the health. Respiratory diseases such as bronchitis are seen to increase with sulfur dioxide levels. Increased level of sulfur oxide in the atmosphere can also degrade agriculture productivity and death of some plants. Nitrogen oxide. Nitrogen oxide are produced in combustion flame of rotated kilns, which enter the atmosphere with the exhaled gases and undergo manipulation in the atmosphere. Majorly, nitrogen oxide is formed by thermal oxidation, which happens in a temperature range between 1200 to 1600 degrees Celsius. Due to high temperatures, significant amount of thermal nitrogen oxide are generated in a kiln. Combustion of nitrogen-bearing fuels such as a certain coal also produce NO, and this is the reaction. As the temperature increases, the NO formation also increase. About 99% of nitrogen oxide are produced in the form of nitric oxide, and remaining 10% are in the form of nitrogen dioxide. Nitrogen oxide causes a wide variety of the health environmental impact because of various compounds and derivatives in the family of nitrogen oxide, including nitrogen dioxide, nitric acid, nitrous oxide, nitrates, and nitric oxide. Similarly to sulfur dioxide, nitrogen oxide reacts with waters and other compounds to form the various acidic compound. When these acidic compounds that are deposited to our surface, they impair the water quality of different water body and acidify the lake and stream. Acidification and chemical changes result in making it difficult for some fishes and other aquatic species to survive, grow, and reproduce. Acid rains can also harm the forest ecosystem by directly damaging the plant tissues. Nitrous oxide is a greenhouse gas and is accumulated in the atmosphere with other greenhouse gases, causing gradual rise in earth temperature. This will lead to the global warming and climate change. Nitrogen oxide and volatile organic compounds react in the atmosphere in the presence of sunlight to form the ground level ozone, which causes the smoke in cities and rural areas. Carbon dioxide and carbon monoxide. Cement industry is a major source of carbon dioxide emission. Carbon dioxide is emitted from the calcination process of limestone and from the combustion of the fuels in kiln. It estimates that half of the carbon dioxide generated from fuel combustions and half originate from decarbonization of raw material. An indirect source of carbon dioxide and other pollutant in cement production is from consumption of electricity, assuming that electricity is generated from fossil fuels. The amount of the carbon dioxide released in calcination can be calculated from components formula weight ratios for the limestone. Carbon dioxide emission from different fuels combustion can be calculated from emission factors of fuel defined by the Intergovernment Panels on Climate Change. The amount of the carbon dioxide emission during this process is directly related to the type of the fuel used, like coal, fuel oil, petcoke, natural gas, alternate fuel. However, the carbon waste materials such as the tires are commonly used in cement kilns to produce its energy content. Process-related carbon dioxide emission from cement production are the second largest source of carbon dioxide emission in the United States. The number of the studies suggested the cement industry contributes only 5% of total anthropogenic carbon dioxide emission worldwide. It has long been known that carbon dioxide emission contribute to climate change. Constantly increasing carbon dioxide emissions are responsible for increase in temperature, which is expected to continue over the coming decades, reaching up to 1.4 degree to 5.8 degrees Celsius globally by the year 2100. Increasing temperatures can cause a severe drought in some of the world, extreme weather conditions, the loss of ecosystem, the potential hazard health, and effect for others. Carbon monoxide can cause harmful health effect by reducing the oxygen delivery to the body organs and tissue, as well as an adverse effect on the cardiovascular and central nervous system. Carbon monoxide can also contribute to the formation of smoke, which can cause a respiratory problem. The emission of carbon dioxide from cement manufacturing sectors can be reduced by improving the energy efficiency of the process, adopting more efficient process, etc. Particulate matters. Particulate matters are emitted from coiling, crushing, grinding of raw materials, and clinker, fuel production, clinker grinding, and cement packaging. Particulate matters is consist of fine particles that can remain suspended in air, which include dust, soot, and liquid droplets. Particulate emission contain potentially harmful toxic metals and compounds such as lead, chromium, nickel, barium, which can pose the serious health impact on human health. The emission are toxic as it carries a carcinogen, mutinogens, immunotoxins, respiratory toxin, neurological toxic, etc. The main route of entry of these particles in the body is a respiratory tract or gastrointestinal tract, or both by inhalation and swallowing. When the particulate matters inhales, they penetrate deep into respiratory system, and the particulate matter less than 2.5 micrometers go into lung and pass into bloodstream. It is determined that short-term exposure to particulate matter significantly increase the risk for cardiovascular and respiratory disease. Particulate matters can also cause the eye and throat irritation, bronchitis, lung damage, increased mortality rates, increased heart ailments. Volatile organic compounds are the slated dioxin, heavy metals, and other pollutants. Other semen-related emissions at risk quantity include volatile organic compound, dioxin, furan, methane, heavy metals. The main source of volatile organic compound emission from cement kaolin is organic matter present in a raw material. Occurrence of volatile organic compound is also associated with incomplete combustion. Volatile organic compounds are precursor to zone formation, which can also contaminate the soil and groundwater. It has been identified that volatile organic compounds can cause the retardation of plant growth, chlorosis, and necrolysis in broadleaf plants. Volatile organic compounds can cause potential health hazards like irritation, respiratory tracts, eyes, headache, damage to livers, kidney, and central nervous system. Heavy metals can affect the plant functions and cell structure. Bioaccumulation of heavy metals can cause poisoning in aquatic and terrestrial life through the biomagnification. Heavy metals can cause damage to brain, nerve system, increase blood pressures, affect on gastrointestinal function, reproduction. Furans can also cause health impact like the skin rashes, liver damage, weight loss, and reduction in immunity. Global warming and climate change, the role of the cement industry. The cement industry has been the major players in global warming and currently still. Why? It is because the manufacturing process is one of the generate lot of the carbon dioxide, and most of which cannot be harnessed. Before the industrial era atmosphere, the carbon dioxide was around 200 ppm. It is now projected to hit 800 ppm by the end for the 21st century. Cement production is thought to contribute 5 to 10% of global anthropogenic carbon dioxide emission. About 40% of the carbon emission from the cement manufacturing come from combustion of fossil fuels in kiln process, while 5% come from roasting of limestone. Several methods of mitigating air pollution and for fostering sustainable manufacture in cement industry have been evaluated in open literature in recent times. Nitrogen oxide emission reducing in cement production. The nitrogen oxide process. In cement industry, method for reducing the nitrogen oxide generated in cement production process can be largely divided into primary control, post-control process based on a combustion stage. Primary control is a method of minimizing the nitrogen oxide generation by changing the combustion conditions, and post-control method is a method of removal of nitrogen oxide generated through the chemical reaction. The primary control to change the combustion condition suppresses the nitrogen oxidation by lowering the oxygen concentration and flame temperature in cement. In a case of primary nitrogen oxide treatment, another air pollutant, carbon monoxide or carbon dioxide is generated. Therefore, this method is undesirable. In addition, although the primary control method optimizes the process to change the condition of the existing process by no change combustion condition control, there is no limit to nitrogen oxide generation, thus it has a maximum reduction efficiency of 60%. So first method for nitrogen oxide removal. Selective non-catalytic reduction of nitrogen oxide. SNCR. SNCR is the most widely used reduction method for reducing the nitrogen oxide in cement production process because nitrogen oxide can be removed simply by supplying the general reducing agents, urea, ammonia without a catalyst. The technology of selective non-catalytic reduction of nitrogen oxide include the injection of aqueous solution of ammonia in the flue gases up to 25% ammonia or aqueous solution of ammonia or urea compounds for the reduction in nitrogen. This is a diagram for the SNCR decarbonization. Biomass currently the fuels used to provide the necessary process heat are mix of the fossil fuels waste, fuels, and biomass. While biomass usage has tripled since 2007, it currently only accounts for the 60% of total fuel mix in the EU. The co-processing of the fuel currently represents nearly half of the fuel used in EU cement industry, with some cement plants reaching the occasional substitution rate of 100%. There are, however, considerable differences between the member states ranging from 6% Greece, 65% Germany, national average co-processing rates, while alternative fuels could provide 100% of thermal energy, fuel substitution of the fossil fuels, while the truly sustainable biomass is technically challenging due to lower calorific value of most organic materials. Moreover, by 2050, competing claims for biomass from other sectors of economy were limited to its availability of cement for cement production. Electrification of the heat, using electricity to provide the processed heat could contribute to decarbonizing the sectors. If the electricity is 100% the fossil fuel free, the cement industry is exploring the several technologies to electrify the cement production, including generating the heat via plasma generators and microwave energy, which have yet to be developed beyond the laboratory. The construction of a pilot plant that uses the plasma technology is currently being investigated. The important possible benefit of electrified heating system is much higher concentration of carbon dioxide in flue gases than with combustion heating, from an estimated 25% carbon dioxide concentration to close to 100%. Hydrogen for the heat. Combustion hydrogen as a fuel can reach the high temperatures required in the cement manufacturing process, but has not been tested, as hydrogen combustions and heat transfer in the kiln would differ significantly from fuels currently used. The extensive research into the modification to the cement kiln would be needed. Then carbon capture. To fully decarbonize the sector, the process's emission from clinker making process need to be regardless of the heat sources. Part of the solution will lead to carbon dioxide capture applied to both the combustion and process emission, or combining a zero carbon dioxide heat source with the capture of concentrated process emission. Several the different breakout technologies are currently being investigated in EU, which are all at TRL, the post-combustion technologies that separate carbon dioxide from flue gases, oxy-fuel combustion, where the fuel is burned in a oxygen rather than air, providing the much higher concentration of carbon dioxide in the flue gases. Calcium looping, which can be integrated into the cement plant or used as a tier and technology, and direct separation technology applied in combination with the zero carbon dioxide heat process. Carbon dioxide storage and utilization contemplated implementation of carbon capture technologies to address the process emission and possible remaining fuels. Combustion emission, the infrastructure to transport, storage, or utilize the carbon dioxide need to be developed. Low carbon cement. The average clinker to cement ratios in EU in 2017 was 75%. European standard differentiate five main categories of cement based on their clinker composition. The most used cement, Portland and Portland composite cement, have clinker contents 95%, 65% respectively. Clinkers can partially substituted by so-called supplementary cementitious materials such as a fly ash from coal power plants and blast furnace slag from steel making. Due to the reduced clinker ratio, the less energy is required for clinker burning and some of the process followed by power and steel sectors. There is a considerable ongoing research on alternative clinkers that emit less carbon dioxide than Portland cement. Next, let's move to the next topic, the technique for carbon dioxide reduction in cement industry. Cement and concrete industry searches for a way to meet the increasing demand while reducing the carbon footprint of the concrete produced. The techniques such as the carbon capture storage, material substitution, alternative fuels, and energy efficient technologies have been identified as some of the approaches to produce more sustainable cement. Carbon capture and storage. Carbon capture and storage technologies, including absorption, membrane-based process, mineral carbonation, and the use of the oxyfuel, have been studied as one of the prominent solutions to minimize carbon dioxide emission in atmosphere. Modified cement products such as the carbon dioxide concrete and several other new technologies, including solid chain technology, carbon rating, and carbon cure, are being examined to minimize the carbon dioxide emission from cement production, thereby making the cement a sustainable construction material. Supplementary cementing materials. Other commonly used approach is a material substitution. See, SCM such as a fly ash slags, limestone border silica from fumes, RHA has been used to partially replace the OPC. These materials helps in removing the performance of concrete either by the pozzolanic or by cementitious reaction. However, all these CMs come with their own limitations. Fly ash is one of the widely used SCM that helps in improving the durability Durability factors of concrete, especially silica reactions, the future viability of fly ash, however, has already been the concern. Limestone dust is another widely used SCM, especially in European countries. The reduced rate aids the trend, however, limits the substitution levels above the 50%, 15%. Nanotechnology. As a recent development, the technology has been introduced in the field to compensate for the limitation of SCM replacement in cement. Nanotechnology is a use of material as a 100% nanomaterials such as a nano silicon dioxide, CaCO3, nano Fe2O3, nano Zr2O3, and nano Al2O3, and nanographites. Nanomaterials change the structure of hydrated base at a nano levels, thereby improving both compressive and flex strength, performance, and durability dramatically. Others. In addition to the above mentioned three approaches, the study have been done on finding the alternative binders to Portland cement, which with reduced environmental impact. For example, instance, the use of low carbon dioxide binders such as the belite aluminative ferrite cement, where the clinkers are based on the belite and raw materials that are rich in calcium. Another alternative binders is alkali activated binders, which commonly consist of two elements, cementitious component and inclined activators. Different industries byproduct and the aluminum silicate raw materials are used as a cementitious material, and sodium silicate is used in activators. The availability and cost of raw materials and technical limitations have restricted their applications. Integrated approaches for producing the new generation cement. If the cement industry were to capture the carbon dioxide, use it to produce nano calcium carbonate within the plant itself, there is a likely the chance the nanotechnology can be applied at commercial scale. The production of nano CaCO3 in the cement plant itself and addition of these nanomaterial is integrated with the cement clinker and will help in reducing the new generation cement. The figures show the schematic flow of the purpose. This figure shows the schematic flow of the purpose approaches for producing the environmental eco-friendly cement. In this approach, the carbon dioxide captured from flue gases coming out of clinker production unit, the captures and purified carbon dioxide will pass through manufacturing chambers where the precipitated nanocalcium carbonate is produced via the chemical synthesis using bottom-up approach. The bottom-up approach will utilize the immediate carbon dioxide in contrast to additional carbon dioxide emission using top-to-down approaches where the energy-intensive process is used for fine grinding of limestone. In the bottom-up approach, the nanocalcium carbonate is produced by passing pure carbon dioxide through continuously stirred aqueous calcium solution and thereby producing the more efficient and uniform precipitated nanomaterials. The source of calcium for this process could either be industrial waste including steel slags, cement and kaolin dust, or calcium chloride from solvay process. The precipitated nano calcium carbonate is added to cement clinker, where the clinkers will be grinded together with the nano calcium carbonate and limestone to produce a supplanting Portland cement with a nano calcium carbonate. The remaining nano CaCO3 will be marked to the industrial, thus generating the economical revenue for the cement plant. This is a schematic flow of proposed integrated approach for producing the next generation cement. Then, environmental benefits. The study shows that if the nanocalcium carbonate were to produce utilizing the captured carbon dioxide from the cement plant and were to replace the Portland cement clinkers with approximately 2% by weight, the carbon dioxide emission would reduce from 0.96 kg carbon dioxide cement to 0.3 kg carbon dioxide, which is approximately 70% reduction. Further, the increase of the structure due to improved durability of cement will help limit the environmental impact from cement manufacturing and construction process. Techno-economic benefits. The integrated approach to cement production solves the two biggest limitations of using nanotechnology in industries. Dispersion and high cost of nanomaterial was ever had improper dispersion of nano calcium carbonates to the high shear actions in clinker mills, thereby improving the concrete performance. Second, the cement plant will have additional source of revenue through the selling of excess nano calcium carbonate to other industries such as plastic, papers, pharmaceutical, rubbers, and only small percentage will go into the intergrinding process. There's a high capital cost installing the carbon dioxide captures and nano the calcium carbonate production unit can be compensated by the extra revenue coming from selling the nano calcium carbonates. Additionally, the nanocalcium carbonate has a high stock market value due to its increasing demands in multiple industries besides the constructions. Then, what are the social benefits of using nanotechnologies? Social benefits: the proposed approach is likely to be accepted by public as it incorporates the multiple stakeholders and industries while providing an access to high quality product at reasonable price. Additionally, the direct and tangible benefit of reduced waste from industries and lower carbon dioxide emissions into environment has greater potential in attracting the social and political interest in this area. Lastly, this technology integrates the new and emerging technologies into existing traditional approaches of cement productions and thereby producing the cement that has a wider applicability. And it's more likely that larger fraction of the society and stakeholders will accept the integrated approaches when compared to other completely novel technologies of cement production with limited applicability. This integrated approaches has thus the integrated approaches thus first avoid the need of storage for carbon dioxide capture carbon dioxide as it will utilize within the cement plant for manufacture of nano calcium carbonate. Second, offset the limitation of the limitation of the SCM, thus allowing for the larger reduction of cement clinkers and thereby reducing the carbon dioxide emission, avoiding the agglomeration issues through proper dispersion of nanomaterials and generate the potential and generate agglomeration issues through proper dispersion of nanomaterials. Fourth one, generate the potential economic revenue to cement industry. All these benefits will lead to the production of next generation cement, thus having to build green infrastructure meeting the goals of global environmental sustainability while also consider the profitability of cement industry. La- Let's now let's move to the next topic, race to zero ambition. So what's the race to zero ambition? It is a global campaign to rally leadership and support from business, cities, region, investors for a healthy zero carbon recovery that prevent future threats, creates the decent jobs, and unlock the inclusive, sustainable growth led by the UNFCCC champions for climate action. It aims to bring together the net zero commitments from cities, business, and investors across the climate action community in the run-up to COP26. Race to Zero collaborates with multiple international networks and the initiatives which have independently been mobilizing the net zero commitments. Global Cement and Concrete Association (GCCA) is becoming an accelerator of United Nations backed Race to Zero campaign. The company is focused on accelerating the halving global emission by 2030 and pledging to reach net zero by 2050. Global construction and building material company CEMES has joined the climate focused initiative business. Ambition for 1.5C and Race to Zero campaign, the company also announced that it has set a new local carbon target for cementitious material sub- submitted it to the same science-based targets initiative for the validation. Building materials companies are coming increasingly in focus on the fight against climate change due to the carbon intensity of their primary products. Cement productions account for approximately 8% of global carbon dioxide emission, 900 kg of carbon dioxide emissions, and generated for every 1000 kg of material produced. For its new target, the CMEX aims to reach below 475 kg of carbon dioxide per ton of cementitious product by 2030. Then references. That's the end of my presentation. Thank you so much for your attention.